interior M plus one dimensional, and sometimes I denote this D, the dimension of the interior manifold. And this is a metric which is satisfied this G plus. And I say it's a conformally compact Einstein manifold. That means there exists a distance function such that this is compact. A defining function. And this metric restricts to the boundary. I call it H. And since the choice of rho is not unique, so this H is defined up to its conformal factor. So we call this is the conformal infinity of this compact Einstein manifold. And yesterday I talked about the specific solution of these Poisson equations, and that's this equation. This is the notation I use. Minus S and minus S, Vs equal to 0. So this is the equation on Xn plus 1. And my Vs has a Poisson data is rho to the n minus s, and this is Dirichlet data identical equal to 1, and plus the lower order term, and then plus the scattering data and the rho s, and that's what I sometimes denote this function by f, the other function by g. So g starts with k and k2 and so on. And the scattering metric S at the index S is equal to n over 2 plus gamma is defined to be mapping the function f to the function g restrict to the boundary. That's the scattering metric. And then this information is an information of, because of this gamma index, this is an operator of order 2 gamma. Pseudo differential operator of order 2 gamma. And so for example, if f is equal to 1 and the function 1 is equal to this is a title, this should be my Q2 gamma, Q curvature. And yesterday I talked about a special choice of f. When f is identically equal to 1, then the function Vs stays positive. And then I choose the particular. So when f is identically equal to 1, Vs is positive, and then the metric, I choose the special defining function to be Vs to the 1 over n minus s power, and then the metric Gs is called this adapted metric, is rho s squared, and then G plus, that's called adapted metric. So this is a family of metric. And then I begin to describe property of this metric, and the 2 examples which I described in detail yesterday is when s equal to n plus 1, this is the Jack-Lee metric, which has the special property if the boundary scalar curvature is positive, the interior scalar curvature is positive. And then when s equal to n over 2 plus 1 half, this scattering metric has the property is scalar flat. And then the special property it has is if the boundary scalar curvature is positive, then its mean curvature on the boundary is positive. Okay, so that's what I discussed yesterday. Today, I will begin to continue to talk about this scattering adapted metric for other index. So the two examples yesterday and today I will talk about a third example, and that's the case when S is equal to n/2 plus gamma. And when gamma is between 1 and 0. And in particular, I will report some recent work of San-Ho Lee, who is a PhD student finishing this year. So we follow the same notation in index. And the first thing is, if this Vs is with Dirichlet data equal to 1, my null index is n/2 plus gamma. So this Sn minus S now is n squared over 4 minus gamma squared. So I look at this solution, and now this index is, there is no F2 and so on. So the thing starts with this rho n minus S, and then the other thing is rho to the 2 gamma. Okay, because 2 gamma is less than 2. So Vs now has the simple expression. It starts with rho to the S power, and then plus rho to the 2 gamma. And then the G there is Q2 gamma. So that's my expression. And the good property of this function is the following. So we have the property of this. First is one can compute using the PDE, this PDE to compute the property. The first property is the scalar curvature with respect to this GS metric, this adapted metric. The scalar curvature is positive on the interior if the scalar curvature on the boundary is positive. Same as before. Okay. And then I write down the expression of the scalar curvature. And from the expression of the scalar curvature, an immediate conclusion is, the scalar curvature is this. It turns out the sign of the scalar curvature depending on gamma bigger than 1 kel or less than 1 kel. So the picture is I have gamma here. This is gamma equal to 0 to gamma equal to 1, and then gamma equal between 1 and 2. And here is gamma equal to 1 kel. And yesterday we discussed at this thing, at this range, gamma equal to 1 kel, this Gn plus 1 kel has scalar curvature equal to 0. It turns out the scalar curvature of the metric is negative here and positive here. So the scalar curvature of GS star is positive when gamma is between 1 to 0, and negative. It depends on the sign. And then the proof also, for that reason, if one compare the expression of RS star to this sign, the immediate conclusion when S is bigger than n/2 plus 2, that means when gamma is bigger than 1 kel, the sign is positive. So in any case, the distance function rho s gradient of that is less than 1. So we get control about the growth of the distance function, rho s less than 1. And I also want to say a word about the proof. The proof is actually, I think, Sanho Li worked on trying to prove this and try various approach. And eventually what he did is he computed the Laplace of this ratio. 1 minus gradient, the distance squared divided by rho to the 2 gamma power, and explicitly compute that, and then using maximum principle. So this is a direct computation. And now I want to describe an application of this example. So an application of this example. And the application I want to describe is a Liouville type rigidity theorem. So let me describe the motivation of this description. Okay, so eventually, I will talk about this tomorrow. Eventually, the goal of this program is to show on a conformally compact Einstein manifold how much the boundary behavior of the metric control the interior behavior of a metric, of a compactified metric. And so the general goal is to show that suppose you have a sequence of metric on the boundary, which is a compact family. I skip a lot of detail, okay? So, but eventually the thing is the compact family on the boundary does not imply the interior compact of some compactified metric. And in general, the existence of H does not imply the uniqueness of this Einstein metric. So this is why we need to study the compactness. And the difficulty of this thing is because of the existence of non-local term. And that is, I mentioned this briefly in yesterday's lecture. The difficulty, say, for example, when n equal to 3 is because the existence of non-local term. And that is, Ray also mentioned this briefly in today's lecture. So in this CC setting, suppose we have this rho, which is a geodesic defining function, given boundary H. Then you have this expansion. This expansion is rho G plus is D rho squared, and then plus a metric H. And this H, say H tilde. And this H, let me call it G rho. And the metric G rho is true to the boundary with my given H. But this G rho has the expansion. Let me describe the case n equal to 3, because otherwise there's other complication. So when rho equal to 3, what you have is the first term is the given function h, and then the second term is what with g1 is equal to 0, and then you have rho square term. This g2 is actually the Ricci curvature of h. But then when you reach G3, when n equal to 3, this is a local term. That is, the behavior of G3 is not described by H, but described by the entire, is a Dirichlet-Neumann operator of a third order. I will give more description tomorrow. And this term is non-local. So the expansion, the first two terms is determined by H, but the third term is not. And so if you want to control for example, if you want to control this G bar is compact, if given H is compact, you must have other information to control this non-local term. That's the difficulty. And so the strategy we use to reach this is we say that we choose special compactification, and we choose the special compactification to be my adapted metric. And then we try to show this H is compact imply the adapted metric, this special choice whose boundary is given H is compact. And the proof of usually to do this is to prove by contradiction. That is, suppose it is not, we begin to dilate the sequence. And so that, for example, the main difficulty is to show the full curvature tensor of the metric GI is bounded, sequence is bounded. And then we say, if it's not, we dilate. And after you dilate, the boundary also dilates. And if HI is originally a compact family, you dilate it, its curvature tends to zero identically. So in that case, the dilated sequence on the boundary tends to Rn dx squared, the flattening. So you are in a situation, the boundary is a flat metric. And so your original sequence now is used under universal cover, live in the upper half space, Rn plus 1 plus. And turns out the key step is to try to show the blow-up limit is the model case, that is the hyperbolic metric. We try to show that. So that's the key step. I will give some description under the some additional assumption this can be achieved. But after we achieve that, suppose we have the picture of this sequence of metric, which is, so the picture now is the following. So the picture is we have this sequence, which is originally defined on HI bar, and then this M, and which under the role of most possible convergence, actually strong convergence, it goes to Rn dx squared. And then suppose, assume the corresponding VC metric on X, which now is under some assumption has limit the hyperbolic metric on the upper half space. That happens under assumption. And then we wonder what is the contradiction. Okay. And the dilated sequence is so chosen, for example, so that the curvature of this dilated sequence, the supernome is 1. So it is equal to 1 at a certain point. Or some point. And then this is the sequence whose curvature is bounded. So you have this sequence on X and with this point fixed, and there is this Gromov positive limit to a metric G infinity bar, and then say on upper half space with certain point, fixed point. So the contradiction would come if we can show this is the flat metric. Is equal to the flat metric. If we can show this, then the curvature of the flat metric at this point p infinity should not be equal to 0. And there is additional regularity. We need, instead of C2, we need C2 alpha. There is an epsilon regularity gain. Under that gain, we reach a contradict to this property that the curvature of G infinity at the point P infinity should be equal to 1. Okay, so that's the contradiction. And the Liouville theorem is to try, this term is what I call Liouville theorem. So to formulate that theorem, we are now in a setting of upper half space, and the limiting function satisfies the same equation, but on the upper half space. And the property we know is this function v, because it comes from the blow-up limit, it's equal to, it's satisfy the hypothesis Vs asymptotically the same as y to the n minus s power. Okay, so Vs on Yns is equal to 1 on the boundary. And we also know the distance function, gradient s rho s is less than equal to 1. And the result we want to say is if Vs is equal to y to the n minus s. So the claim is correspond to the following proof. So the theorem is, now we are on hyperbolic space, and we have this equation, the star S equation, and then we wonder if Vs satisfy this star S equation, and then if we know Vs on the boundary is equal to 1, and if Vs is positive, and if gradient with respect to this metric, rho s is less than 1, so this rho will lead to the 1 over n minus s power. Is that, does that imply Vs is equal to y to the n minus s power? So if we want to look at this solution, so that's the question. But since this is, there is already originally 2 indexes, so for example, without this additional hypothesis, there are other solutions. And the other solution is y to the s power. So you have a linear combination of this solution, and there may be other solution. So the problem is, why this other factor is not there? So the question is, does that imply Vs equal to y to the n minus s power? So that's what I call Liouville theorem. And so to prove that, it turns that's a theorem of Sanho Lee. What he proved is indeed this is the case when gamma is between 1 and 0. Okay, so if we have, this could be a general question for any s, but if s is equal to n over 2 gamma, gamma is between 0 and 1. And then we try to show this is the case. And it turns out he also add additional condition. So the theorem is plus, so this is the hypothesis. So this is hypothesis 1, hypothesis 2, hypothesis 3. And in Chang-Li's result, we also add hypothesis 4. So let me describe the hypothesis 4. So what is the hypothesis 4? So remember that yesterday we first relate the solution of the Poisson equation on the Hopper-Held space to this weighted Laplacian. And that is, if you look at this function u, which is equal to Vs to the y to the s minus m power. So this Us on the boundary is equal to 1. And the observation is this Vs satisfies this star s if and only if it is satisfied this Laplace Au equal to 0. This Laplace A is the ordinary Laplace plus A over y dy of the weighted. So it satisfies this equation. And so the question equivalent for Vs to be equal to y to the n minus s, the question is, the equivalent question is Us identical or equal to 1? On the boundary, it's equal to 1. It satisfies this Laplace Au equal to 0. Is it always equal to 1? So we can transform to that question. And Chang-Li's theorem is assume he used the notation W equal to 1 minus U. We know Ws. So this Ws is on the boundary is equal to 0. And then it is U is bigger than, so this Ws is on the boundary is equal to 0, and it's always less than, Us is positive, so it's less than 1. And the problem is, does that imply Ws is identical to 0? So this Us and Ws is just different by 1. And the condition he had is, he assumed A1, assume W is in H1A local with respect to dx dy. So this is a W1A derivative, and then, so this means the gradient U square y to the eighth power is finite, but it's only in the local sense. For each domain, bounded domain in Rn, you have this property. Rn plus 1 plus, you have property. So the theorem is, this is true. The theorem is, this is true. So let me say a few words about his proof. So the proof have 2 stages based on 2 observations. The first observation is you transfer the proof, so proof has 2 stages. The first lemma is to say this gradient s rho s is less than 1 correspond to say Ws, we originally know it's less than 1, and it's on the boundary is equal to 0, And this condition tells you it's greater than or equal to 0 on X. And which turns out to be a computation. Okay. The only thing one uses is let me recall that this gradient g of any function f is recall this is equal to gij fi fj in local coordinate. So for that reason, you can, if you use a conformal change of g, then that square is just 3 minus 2, the change of f. Okay. So for our problem, you just try to change, so you rewrite this, your gs star is equal to this rho s squared times g plus, and in our case, this gh is hyperbolic metric, so you write this as y squared and g flat metric. And then every computation reduced using this transformation rule, reduced to computation on the flat metric. And that's what this is about. So what happens is this implies dy of ws is less than equal to 0, greater than equal to 0. And then this would imply, and on the boundary it's equal to 0, so it's between 1 and 0. So it's a boundary function. And then the second part is he tried to use this weighted space. And one fact is a fact which he pointed out in a recent paper by Sale, Terracina, and Vita. And the observation is for this specific index, y to the eighth power, so the second line is when a is between 1 and minus 1, this y to the a is in the Munkenhof A2 weights. And weights of this type behavior has been well studied, and in particular, one can use the density function to study it. So the conclusion is, if this Laplace AW is equal to 0, and if it's in this weighted space, and if it's bounded on Rn is equal to 0, if it's bounded, it's identical to 0. Okay, and the proof uses this density weight, and that is, you consider this function h, which is a weighted space on the upper half space. That is, I'm sorry, on the ball of radius r on the boundary hr. And then consider the energy. The energy is y over r to the n plus 1 and then br plus. Okay, so that's this function. And one observation is this way is added. So both these terms are scale invariant. So that means that if you change r to lambda times r and z to lambda times z, I'm sorry, lambda times z, and w of z to w of lambda z, then the expression of h and e are the same. And based on that expression, one can compute the derivative of h with respect to r. So there is this HR definition. And then one compute h prime of r. And usually, if you look at the expression of h, if one wants to compute this h prime of r, it's quite involving. But using the scale invariant property, one can rescale the metric, so the computation only happens on the interior. That is, you can stay the same R to the n plus A and then compute only dr of W squared. Okay. And then that computation you use directly and you substituting into the equation Laplace AW equal to 0. And the key point is this is equal to 2 over R dr. This strategy has been used a lot in the study of harmonic function, the zeros of harmonic function, and so on. Okay, so this h prime of R is 2 over R of E of R. And then one gets an inequality that if one look at this E of R, which is equal to YA gradient W squared, and remember W on the boundary is 0. So using this property, one can compute using Hardy's inequality. So it turns out this E of R is greater than equal to H of R over R. I mean, E of R is greater than CA times H of R. Okay. And this CA is 1 minus A over 2. So when A is less than 1, this C of A is positive. So that's a Hardy inequality. And thus, what we have is H prime of R is greater than equal to C of A for some positive function A of H of R. So that gives you some growth of H of R, and then this is monotonic. So H prime of R divided by H of R, I mean, weighted H of R is R to the minus CA, H of R is positive. And so H of 1 is less than, at the point if R is bigger than 1, H of 1 will be less than equal to R to the minus CA H of R. And if one examines that inequality, which shows that this, you write down what is H1, and then you write down what is H of R, and then you move R to the n plus A to the other side, and use the property W is less than equal to 1, then you have this function R to the CA plus n plus A to this integration is less than R to the n A to plus n, and you let R go to infinity, which pushes this W to be identically 0, and that's the proof. Okay, so this is so use this show that W is identically 0. So that's the second one. So that's the proof. And let me just remark that this result potentially could be true for any gamma. At this moment, it's only established for gamma between 1 and 0. Okay. So in general, one can ask, suppose you have this Poisson equation, suppose you know the metric has positive scalar curvature, does that imply you already have this V is equal to y to the n minus s power? So, and that's the proof. And for gamma bigger than 1, the question is open. And for the rest of our talk today, I also want to mention a fourth example. So this is example 3. And the fourth example, I finally want to move to gamma bigger than 1. So when gamma bigger than 1, now gamma is bigger than 1, so gamma special case, gamma equal to 3/2. This strategy eventually would work for gamma between 2 and 1. So let me talk about gamma equal to 3/2. And since our metric is not always defined in n/2 to infinity, but not at the integer point n, so this is when n not equal to 3. Okay, so in this case, we have, when we want to study the solution of the equation n squared. The equation is n squared or -9/4 is Dirichlet data f equal to 1. So that's the equation we want to study. Okay, so to study this equation, it turns out we need our strategy is we use the help of the fourth order Penny's operator. So let me first mention a little bit of background here. And what is the fourth order Penny's operator? This Penny's operator, remember, it all have conformal covariant property. So on dimension D, the fourth order Penny's operator or GJMS operator, the leading symbol is by Laplace. And then there is lower order, first order derivative term in terms of the scalar curvature and Ricci divergence delta. So this is a second derivative of the curvature. And then there is a d minus 4/2, and then it's a Q curvature. Okay, and notice that when d is not equal to 4, P4 at the point 1, you capture the Q curvature. Okay. But when turns out this expression also holds when d equal to 4. So one write down the P4 operator in 4 dimensions. And Bronson pointed out, in this case, when dimension equal to 4, although you do not see Q4 from P4, nevertheless, Q4 is well defined. And you use the dimension continuation argument of the expression of Q4, you can write down Q4. Okay, so P4 is related to Q4. Let me put it that way. And the Q4 has the nice expression is minus Laplace scalar plus R squared minus 3 Ricci squared. This is a Bronson's Q curvature. Now, the connection to what we are doing here is on a metric G plus with Ricci equal to minus NG plus. In general, this expression involves the curvature computation scalar Ricci of the metric, but for such a simple Einstein metric, you can compute. And it turns out this P4 for this metric is a composition of the P2 and then Laplace G plus minus n squared minus 9/4. Thus, observation is this implies P4 of G plus Ds is equal to 0. Okay, so it satisfies this. Okay. And a fact which is not completely obvious is it turns out these are equivalent. If something satisfies P4 G plus equal to 0 in this CCE setting, and if one already have a Dirichlet data, and then one also have this expression y to the h power d dv is equal to 0, so there's an implicit Neumann condition built in that makes the solution unique. So these two are equivalent. Okay. But on the other hand, we only use this direction at this stage. And this PD on this fact, a remark is, the corresponding fact of this fact that you have a second order PDE is satisfied by a fourth order PDE on the standard flat space Rn plus 1 plus, or for this dx squared plus dy squared, the flat space, this fact corresponds to if Laplace AU equal to 0, implies Laplace B squared U equal to 0. If A equal to 1 minus 2 gamma, and B is equal to 3 minus 2 gamma. Okay. So a solution satisfies second order PDE, satisfies a fourth order PDE. So we use that. And using that fact, let me list some property of this adapted matrix. The first important property is its Q4 curvature is identical to 0. Okay, and this is a direct consequence of, so the property is the first property is Q4, the d-dimensional curvature is identical to 0. And this just use the conformal transformation rule, conformal covariant property, and notice the index n minus s happen to be d minus 4 over 2, where d is n plus 1. Okay, so this is just algebra. And I use conformal transformation rule. But then there is another non-trivial property. The non-trivial property is if the boundary of scalar curvature is positive, this would imply this scalar curvature of this GS star is also positive on X. So remember, this is a property of the Jet-B matrix, and it turns out it's a common property for all S equal to n over 2 plus gamma, when gamma is bigger than 1 half. So this is a common property. And after that, the basic thing we will use is this property imply the distance function is controlled. So this implies the distance function GS of rho S is less than equal to 1. And that's an important property when we reach compactness. So let me remark that at this moment, I want to say that it turns out for all adapted metric, when S is between n over 2 plus 1 half to n plus 1, one can use continuation method to show that the scalar curvature of GS star is always positive. Okay, and this is a theorem observed by myself and Jeffrey Case. And before explaining why this is so, let me also remark what happened when n equal to 3. So this is for S n not equal to 3. When n equal to 3, it turns out the scattering operator has a pole there. Now one need to take the residue of that and then compute this thing. So one need so this when n equal to 3, the standard solution of GS of VS now, this index becomes 0. So if this is a Dirichlet data 1 plus something, the Dirichlet data is equal to 1, and this case n equal to 3, S equal to And so this is just rho plus something. And in this case, one can show that function is identically equal to rho. That's the only solution. I'm sorry, I'm a little bit confused, but this is the only solution. So there is no theorem, no behavior one need to consider, but instead one should take this is the idea of Pfefferman and Graham. They say that in this case, the correct PDE to look at is to take the derivative of this Poisson equation and compute so you look at W, which is minus DDS of VS, and evaluate at the point S equal to N, and you get to this equation, which is, you differentiate this DVS of this star S equation, VS, and evaluate as S equal to N, and that's called W. And this W using the PDE will satisfy W is equal to N. And the metric G star, we call it the Pfefferman-Graham metric. And so one should apply this analysis to this metric instead of the adapted metric, which I talk about, and it still has Q curvature equal to 0. Okay, Q curvature equal to 0. In this case, you also use conformal transformation rule. So in that case, Q equal to 0 means Laplace of the scalar is equal to scalar minus 3 Ricci square, and I tend to write it in terms of traces Ricci, so that's the PDE. Okay, given that understanding, we now have, so the theorem I want to briefly describe is terms of so this is a result of Jeffrey case earlier. And what we show is when S is between N plus 2 plus 1 half to N plus 1, this metric are all totally geodesic. Not including 1 half. At 1 half, the scalar is 0. All of these are S of G S star is positive. The boundary metric is positive. And I will not go into detail, but let me say that this is an interpolating result. And so recall that at the index N plus 1 star, you have the PDE, which is in terms of the curvature, the PDE one write down is this Laplace of scalar is equal to minus of the original proof of Lie is showing Laplace of the scalar is minus of the traceless square. And then that's at S equal to N plus 1. And at S equal to N, we have this Pfefferman-Graham metric, which is also Laplace R equal to a combination of scalar square minus Ricci square with different constant. So the result is an interpolating result in between. So it turns out that the PDE satisfied is this PDE. So we rewrite this, so the proof is 1i. We rewrite this equation in terms of the curvature. And in terms of the curvature, it turns out this is the PDE, which I wrote down there. which is divergence rho to the minus m and rho m and gradient of r. And then it's a combination of the scalar square minus the trace hysteresis square. And one can compute the precise coefficient ASBS. And this coefficient turns out on a range which I am interested is all positive, ASBS, all positive. And at the end point, s equal to 1, the A coefficient is 0. So you get Laplace of R is negative. And then at the other index, you all have positive coefficient. Okay, and this M is equal to, so we have this equation, Laplace M, and then, I'm sorry, I forgot this equation, Laplace M, and then rho M divergence of T, rho M, and gradient T of R equal to A times R squared minus B times trace hysteresis squared. That's a direct computation. And using this computation, we can show that it's by continuation method that this scalar curvature is positive. And the way to show the continuation method is you have this range S equal to n plus 1. At this point, you already show the scalar is positive. You want to reach n over 2 plus 1 half. Okay. So you say that your scalar curvature starts positive until it stays positive until it hits a point where the scalar reaches 0. And then you will say that since you already know the boundary curvature scalar is positive, so the point it reaches 0 is at the interior point. Okay, and at the interior point, it's if it's less than 0, then the minimum is less than 0, and then this PDE tells you that at a point where this R is, say, equal to 0, and then this B, so at the interior minimum point, you are supposed to have the Laplacian R positive, but at this point it happens to be negative when R reaches 0. And then, so that would say that this violate maximum principle, interior maximum principle says R is identical to 0, which is not possible because we already know the function on the boundary is positive. So this is a continuation argument. So anyway, so this turns out to be a family of metric all have scalar curvature positive. And for the purpose of this meeting, especially I think the talk next week will have a lot to do with the notion of renormalized volume. So let me mention another application of using the Q curvature to study the renormalized volume. Okay, so let me define. I will briefly sketch the idea, and there's a lot of content about this renormalized volume. So there's this notation of renormalized volume introduced by Wheaton and Madassina and Graham, Robin Graham in I think in in around 2000. Okay, so the idea is to study the volume of this rho bigger than epsilon. Okay, look at the asymptotic behavior of rho bigger than epsilon, and it starts with epsilon to the minus n power And then it has, in the CCE setting, it only has epsilon square, epsilon 2k term, minus n plus 2k term. So when n is odd, it reaches epsilon minus 1. The next term is called the renormalized volume. So the renormalized volume means you take out a part of the volume which is blow up as epsilon tend to 0. You look at the first term, which is non-zero, and that's called renormalized volume. And then when n is even, this asymptotic behavior has log 1 over epsilon term adding, and the next term is called renormalized volume. Okay. And the most important result I want to quote is a result I learned from Robin Grant's paper, which says that when n is odd, this renormalized volume is a conformal invariant term. That means this definition is independent of the particular row you choose. Okay, you have this different distance function, defining function. You use, if you change row, your coefficient C0, C2 in front of this 1 over epsilon or depending on this row, but not this renormalized volume term. And when n is even, it turns out in conformal invariant term is L. Okay, so this is a very brief introduction of renormalized volume. So the theorem I want to quote is when n is even, in a paper by Robin Grant and M.Zworski, and also later by Pfefferman and Grant, although the publication date somehow Pfefferman Grant paper appeared first, but the first paper is Grant and M.Zworski. They show that when n is even, this in conformally invariant term is integration of the nth order Q curvature, Qn. Okay, and now when n is odd, what is this renormalized volume term? I want to mention a result of Anderson. Okay, so the Anderson result is to say on this CCE setting, we have this A pi square Euler characteristic of X4 is the same up to the L2 norm of the Weyl curvature, the six times the renormalized volume term. So here's the theorem of Anderson. This is a line Anderson. And what they say is A pi square Euler characteristic of X4 in this compact setting is equal to 1/4 of the Weyl square and plus 6 of the normalized volume. And if we compare this formula to the Gauss-Bonnet formula, Gauss-Bonnet formula says, suppose we have a metric G here. And this G, if G, so we are now talking about a full manifold with boundary. So this is CC setting. On compact case G. And then we have this is the same as Weyl square. And then if we compare the coefficient, the next thing is 6 times R squared minus 3 of VC squared. And then plus a bunch of boundary terms. Now let me not describe that. That's the Gauss-Bonnet formula. And so in particular, when G is totally geodesic. This BG term is identical to 0. So you have only these two terms left. So if you compare these two formulas, that says this renormalized volume is the same as that expression. Square minus 3 VC squared. And notice that our Q curvature has the same expression, except we have minus Laplace R term there. So that means that we can somehow use the property of Q flat metric to derive the renormalized volume. And that's achieved by the following two lemmas. Okay, so the first lemma is, say, for simplicity, I'm now talking, some of the lemma are true for general N, but in general, I only talk about N equal to 3 case. The first lemma is to look at the asymptotic behavior of this Laplace W equal to N on X N plus 1. Okay, when N equal to 3 is X4. And then this W has asymptotic behavior, log rho plus A plus B to the rho to the nth power. And this A on the boundary is equal to 0. And there is a lemma of Pfefferman-Graham in their paper. They show this V renormalized volume is nothing but the coefficient of B on the boundary. B on the boundary. Okay. So I'll improve this. Different proof. And this is by myself and Qingjie and Yang. 6. And so what we did is consider this solution. So the first lemma is actually Pfefferman-Graham's lemma. They study this equation. And saying that under the Dirichlet data condition, it's A plus B plus rho to the nth power asymptotic. And then their theorem is this renormalized volume is nothing but integration of B with strictly the boundary. This integration is the same. Okay. And the proof actually is one line. The proof is actually just one line. And that's because you are interested to consider the volume of G plus of rho greater than epsilon. So, but your equation is minus Laplace W equal to N. So that's just the integration of this Laplace W. And then this Green's formula tells you you can compute Laplace to its normal derivative on the boundary. And because of this G plus, you have epsilon to the 1 minus nth power in front of rho equal to epsilon coefficient. And then plus the contribution from rho equal to rho naught 10, and that's a finite. That's something which you can control. And then, so the renormalized volume, remember, is the constant term in this expression. So that means in computing dWdn, we only need to pay attention to the term which is of order n minus 1. And if you look at the expression of W there, then dWdn the n-1 coefficient is the number B. Okay, and that's the proof. Okay. So this is lemma 1. And then lemma 2 is the computation. If we look at the metric, we look at that metric, and then this expression, we can compute B. This B turns out to be 1/6 dp normal of scalar curvature of B star. Okay, and I just computed because one have this PDE. And then, so this renormalize, so the proof of the theorem reduced to the following line. That is, you have renormalized volume equal to B, and that's equal to up to this coefficient, the normal derivative for B of scalar. So this is the same as Laplace R on the interior same coefficient. Okay, Laplace R. And this Laplace R, if you look at this Q4 is identically equal to 0, then this Laplace R is that multiple of this VC squared. And that's the proof. So that shows that at least for this metric, G star metric, the renormalized volume is this expression. But once you have proved it for one representative of G, the other thing, if it's also totally geodesic, both sides are conformal invariant quantities, so they are the same. Okay, so once you establish this theorem for G star and for any other totally geodesic metric, it's the same expression, and that's the proof. And this proof has the advantage that it's a simple proof, and it also has the advantage it can be generalized to n dimensions. And it turns out that this renormalized volume for any odd dimension, n-odd, can be written as this expression, what we call Vn plus 1. This V has nothing to do with solution. This is just a notation. What is that Vn plus 1? V2 is the first symmetric function of the Shelton tensor. Okay, so let me not go into detail. So there's Shelton tensor, which is well studied in conformal geometry. And one trick is elementary symmetric function, that's V2. And V4 is sigma 2. And sigma 2 is this expression. So that's the sigma. It's always the same. But this comparison ends at when n is bigger than 3. When n is n plus 1 is bigger than 4. It turns out for locally conformally flat metric, that's those metric whose value is equal to 0. This V2k is a multiple of sigma k. The k is elementary symmetric function. But when k is bigger than 2, there's correction term. And when the metric is not locally conformally flat, there is correction term. For example, when k equal to 3, V6 is sigma 3 plus some composition of the Shelton tensor with Bach tensor. Okay, so there is correction term. But inductively, this V2k all are known, and that's by lengthy computation by Joule and also by Pfefferman and Graham. There is inductive formula to compute all these Vk. And this Vk comes up naturally in this subject because the volume expansion of G rho to G0, the flat metric, has the coefficient rho to the 2k power, this particular curvature V to the 2k. Okay, and so our theorem is you can write down the renormalized volume in terms of this Vn plus 1, and for any totally geodesic metric. Okay. Okay. I have 15 minutes, and now let me change the subject and talk about another topic, and that is comparison of Yamabe constant on boundary metric and on interior metric. Okay, so I only want to discuss this in a CCE setting. So in general, suppose we have a compact closed manifold, we have this Yamabe constant, which is, I like to consider it as a second order conformal invariant. So this is a scalar curvature and then normalized by the volume. So this term is scale invariant. So this is a Yamabe constant. Now, if M is a boundary of another manifold, xn plus 1, then suppose we have this compactified matrix G plus, then we have two different types of Yamabe constant, and type 1 constant and type 2 constant. The type 1 constant is the scalar plus the mean curvature and normalize the volume in the interior. Okay. And then the second Yamabe constant is normalize the boundary metric, volume of the boundary metric. And both this Yamabe constant, whether it's achieved and the extremal metric have been well studied, mainly by Escobar, but there are a lot of other people. And this theorem, in this CCE setting, what we have is, if the Yamabe constant on the boundary is positive, then the Yamabe, the Y1 constant on the interior is positive, is greater than or equal to 0. Then a natural question we are asking is, can we quantify this expression? That is, if the Yamabe metric on the boundary is strictly positive, do we have the Y1 greater than or equal to some constant depending on its delta? Okay, quantify. Why do we care about that? Why do we want this Yamabe constant to be strictly positive? And that's because in the iteration scheme, later on, when we look at this conformal factor, the growth of it, we iterate the metric. And when we iterate the metric, the Yamabe constant acting as Sobolev constant, Sobolev embedding. So we want the control of that embedding Sobolev constant. So this is a question we want to say the embedding constant of H1 to L2n over n minus 2 is nicely controlled. Okay. Okay. Now let me mention 3 results in this subject. The first is a result of Zworski and Han. They are working on other problems, which I will briefly mention tomorrow. And this is one of their results. And they say that indeed this Y1 constant is greater than or equal to Y on the boundary, but there is this isoperimetric constant on the interior. So this isoperimetric constant is volume on the boundary divided by to the 1 over d minus 1 power divided by volume on the interior. So there is an isoperimetric constant. Okay, and this is for d bigger than or equal to 4. And for D equal to 3, there's other version. Okay, so we know y1 is bigger than y, but then there is this isoperimetric constant. And even for the extremal metric, say the Yamabe metric on the interior, we do not know the ratio between the Yamabe metric on the volume in the inside to the volume on the boundary. We do not know if we control if that thing has an upper bound. So this result shows that if y is positive, y1 is positive, but it doesn't really show if m is positive, y1 is strictly positive. Doesn't show that. And then there is a second result by the three authors, CHANG, Lai, and Fan Wang. Okay, this is a team of workers in China. And they say that if y is positive, then its y2 square is bounded by y. So this does show if y on the boundary is positive, then y2 is strictly positive. And let me also mention that in both cases, in Gursky-Heinz inequality and in these three also constant, this inequality, this constant all are sharp. And one can identify its extremum case. And now there is a recent observation by Yishinger and I. What we observe is 1 and 2, y1 bigger than y and up to this isoperimetric constant, and 2, y2 bigger than y, would imply y1 is bigger than some constant times y to the d minus 1 over d power. So, but since our observation is combined 1 and 2, this constant is not sharp. We know it's not sharp. Okay, it's not sharp. So if one sit down and one can work out the proof, maybe more easily than the way I present it here. But let me say that the proof is just the observation that we are looking at constants which are invariant, scale invariant constant. So what the idea is to use the extremal metric in 1 and rescale it and use that as a testing function in the second inequality. Okay. And so the proof boils down to the following line. Say, suppose we have a Yamabe metric on the interior. So that means scalar is equal to constant, mean curvature equal to 0. Okay, I'm sorry. Before I show proposition 3, I want to say, Matt, pay attention. Okay, so I want to say a word about your proof and a new way to visualize your proof. Okay, so Matt's proof is application of Obata's result to this CCE setting. So he looked at traceless Ricci E. By the way, I'm willing to share my notes, whatever who of you is interested. Okay, so the proof is written here. So he looked at rho times this traceless Ricci square, and Obata's trick is if G is Einstein, and then any metric which is conformal to G also is Einstein, and he used that to show rho EG square is 0. But Matt's proof is use the same strategy to write down this metric in the CCE setting, and then examine carefully this identity and show this constant is that isoperimetric constant. And while playing with it, we notice that there is another proof. Yeah, that in studying this scalar curvature of this adapted metric in the special case when the gamma equal to 1 half, their scalar curvature is equal to 0. And then there is this proof of Fan Wang. We examine carefully her proof, and we find out there is actually a magic identity which applies for all CCE settings. And that is, if the scalar curvature of a metric is a constant, then, for example, for the Yamabe metric or for the scalar flat metric when R is 0, we actually, for the metric G plus, where G is rho square G plus, there is an identity. That is this Laplace G of 1 minus gradient rho square divided by rho and minus this scalar curvature times rho. The 12 has something to do with D equal to 4. There's a dimension constant is equal to rho over 2 EG squared. Okay, that's an identity, forever true. So if I integrate that, we won't get you equality. And this is a pointwise computation. Okay. And integrate that, we get this. And when R is a constant, and the observation is when R is a constant, this R can also be written as Laplace over rho minus that number. So if you plug in that, anyway, it's a algebraic proof. You get its identity. So that's proposition 1. Let me finish my talk today by sketch a proof of proposition 3. As I say, the proof is choose the right representative, use rescale property of this quantity, the isoperimetric constant quantity, and use that as a testing function for Y2, and plug in the second inequality, then you get identity. I have written down the proof. I don't think I should go into detail. Okay. And an open question, which I find interesting, is what is the sharp constant in this third inequality? If you want to compare the Yamabe constant on the interior to the boundary, what is the sharp constant? Here is a guess. Okay. And the guess is, I think the right strategy will be to look at the quotient. Okay. So my guess is the Yamabe constant of Y1 on this D-dimensional setting should compare with the model case. The model case is the upper half ball with S n-1 on the boundary. And that constant, the ratio of that constant should be greater than equal to the ratio of the boundary Yamabe constant divided by the Yamabe constant on the standard model too. And that should be the natural constant, but I don't know how to prove that. Okay, so that's my guess. Thank you. Thank you.
Questions? Yeah, your guess here at the end.
Yes.
Isn't that close? Isn't that known for, you know, that the boundary, the use measure? That's very familiar. I mean, I thought there was this volume rigidity talking through.
So that means the constant is y1 of s plus d. If you want y1 bigger than y to the power, that constant is y of sd, and then ratio between y1
Yeah, I was asking, is that inequality actually known if, say, G bar is close to the round metric?
That's right. That's right. This G bar is with the boundary H, and that's a Yamabe constant. So I just write it in terms of conformal class. Yeah. Okay. Okay. Sure. Yeah.
Okay, Doc, let's think else together. Until 4 o'clock, right? Let me make more clear what I was trying to ask. So there's in his paper, it's by Chang and my course.
Okay, so those of you who asked for the menu at the canteen, I have the ticket. So I'll be outside, so you come to me.